welcome back to another round of PyCon sessions. I hope you've all had a good break and that you're ready for another block of amazing talks. I do have a programming note here, which is that Tessa Bradbury, who was going to be talking about open telemetry here, unfortunately could not make it. And luckily, Noah was able to step in, and he's going to talk about the long hello world now. Give him a big round of applause, and then we'll get going.
All right. As I said, I am Noah Kantrowitz. I'm an SRE at Geomagical Labs, which is a part of IKEA. I do computer vision and augmented reality stuff for IKEA, but I'm not here to talk about that today. Hello World is a starting point. Now, most of the time, it's a starting point for talking about functions and strings and all of programming, but we're going to use it as a starting point for something else. Rather than looking outward, we're going to look at the stack below this. We're going to look inward at all of the moving pieces that make up this innocuous line of code. To set the stage a bit, we're going to look at the specific case of Linux and glibc. Python runs on many other platforms and combinations, but we want to look at specifics, so we've got to pick one. All code samples are correct as of writing in September 2025. If you're watching this in a video in the future, please check the repositories. And our point of departure, we are in a Python interactive shell. We have typed in print hello world, and we have just pressed enter. What happens next? Not saying it prints hello world. What really happens next? This is our first stop, slightly simplified. The heart of the interactive interpreter is going to be a while loop that it's calling input, gets our line of code, which in this case is going to be print hello world, and then it does something with it. In this case, calling self.push. Every one of these layers is going to involve a lot of calls, so we're going to skip around a little bit, just so this doesn't take hours, but following down the call stack from that push method, here's the part we care about. We have the code, and we're going to call the exec built in on it. This is going to parse and execute our line of code. What does that mean? It's theoretically possible to build a language which just executes code one byte at a time, but this makes any kind of complex syntax really hard to implement. So basically all major languages go through a number of steps to add additional information to the code as it goes through the processing. Decoding bytes to Unicode characters technically happens first, but that's been covered many times in many places, so let's look at the other steps in a little more detail. Lexing or tokenizing, which is the same thing, just different words, that's the step that goes from a sequence of characters to a sequence of tokens. We'll talk about tokens. And then parsing turns a list of tokens into a syntax tree. To reach the lexer, we need to jump a ways down the stack. And in practical terms, the lexer is actually more like a Python generator, although it is written in C. It produces tokens on demand as the parser needs it. But toke get normal mode is the bulk of the logic. So what's this going to do? It's going to go through each character one at a time, group them together, and tag them with, this is the kind of thing that this is. The token module in the standard library exposes all of the available token types, so we can see a few kinds of patterns here. So the first are names. This is anything that looks like an identifier, function names, variable names, class names. Numbers and strings, those are just literals. And then syntactically significant punctuation, parentheses, colons, the plus sign. The lexer also emits indent and dedent tokens, so that the parser doesn't have to care about tabs versus spaces. And this is where line continuations happen, again, just so the parser doesn't have to worry about that. The tokenize module lets us experiment with a lexer and see the resulting token list on the command line. So let's feed it our line of code. We end up with 6 tokens. So the first is a name token, which matches up with the characters P, R, I, N, and T. Then a left paren token with the left paren character. Then our string literal token, a right paren, a new line, and an end of input token, which is just an opaque way of saying you have run out of input. This is more structured than our original string. We know a little bit more about what's going on here, but this isn't really ready to execute as code. We've still got parsing to go. So far, the representations we've been talking about have been linear, a sequence of bytes, then a sequence of characters, then a sequence of tokens. But when we think about complex code, it's not really flat. We would think about the body of a function being inside the function definition, or the parameters for a function call are inside the function call. An abstract syntax tree extends this concept. So we want to build it up as a recursive tree of all of the syntax in our code. Python's parser is built around a parsing expression grammar, or PEG input. This file, python.gram, it has all of the different syntax of Python in terms of the tokens we saw before. Now, parsing is an incredibly dense topic. This is going to be a surface level read on all of these pieces. So the short version is that we want to match them from left to right in a particular order. Each grammar rule will then say what type of syntax node to create and has a little bit of extra information about how to recurse down into the next piece of syntax that it should be parsing for. In the end, we end up with this tree structure that is our abstract syntax tree for the code. As with the tokenizer before it, we have a command line module we can use to play around here. So we pass our code into the AST module. We end up with a module containing a single expression, which is a call with a name of print and a single argument with a constant of hello world. Now, this is as structured as Python code gets and is ready to march forward on its journey towards running. Many words have been said over the years about how Python is or isn't an interpreted language, and obviously I've lost interest at this point, but we can show very clearly here that Python is a compiled language because our next stop is the Python compiler. And before we can talk about compiling Python, what is that compiler for? Now, when we compile C code, we are emitting CPU instructions for the physical hardware in your machine. CPython has what's called a virtual machine. Now, this is different than a virtual machine like running Windows on your Mac laptop, but it's the same idea of being a very fancy fake computer that we can write instructions for. The core of the CPython virtual machine is the stack. If you've worked with Forth or an RPN calculator before, you are one, very old, but two, this might look familiar. In a stack-based system, basically every operation is one of three things. You are either pushing something onto the stack, you are operating on the top of the stack, or you are popping something from the stack. CPython does track some additional things, call frame metadata, thread state, stuff like that, but the heart of it is really the stack. And because our virtual machine can be way more complicated than any physical computer we could build, our low-level instructions can be pretty specific to Python's patterns. They're called opcodes, and they are the building blocks of all of Python. The dis module documentation lists all of them, and here's a few to just set the tone. You can see they vary widely in complexity from that simple push-pop to as complicated as create a generator object. That is one assembly instruction as far as Python is concerned. New opcodes get added as new features are added, old ones are removed. At any given time, there's usually about 100 Python opcodes. Okay, so we're back into run mod in python run.c, and we want to call down into the compiler. Again, this is just showing the call stack from top to bottom. The core of the code gen system, which is the heart of the compiler, is a visitor pattern. So it's going to walk down the tree, and it has a callback for each type of syntax node that the parser can emit. With each of those nodes, it's going to create 0 or more opcodes and push them into a code object that'll eventually get bundled into a function, which will get bundled into something else like a module. Again, the compiler could be a whole talk, but let's just look at our bytecode for our hello world. Again, the dis module has a command line interface just like the other two so that we can pass our code in and see what bytecode we get out. So we end up with these opcodes. Load name, looking for something called print, then a push null. This is new in 3.13 because the calling convention changed. All that is saying Python doesn't actually take a self argument, so we just give it none instead. Then we load our hello world constant string, then we call the function, print. We ignore the return value because we don't care if print fails, and then we return none because everything in Python has to return something. All right, finally, this is a program. We can actually run this. So we're back in run mod, but we're going to descend down a different piece of the code tree. We're looking for the part of Python that actually runs this stuff. This leads us to the function pyeval, eval frame default, which is possibly the most complicated C function in all of Python. This function and its friends unpack each compiled opcode and perform whatever computation it requires. So, as an example, here's a little bit of how the load name opcode is implemented. We've got a little bit of weird stuff with stack things, but the core of it is the bottom three lines. We call pyeval load name to get some kind of object, and then we push that object into the stack. This is also where the JIT happens, and I wanted to show some code samples, but honestly the JIT is spread out over a million places, and there isn't really one thing to show you. So the really quick version, whenever a jump backwards opcode is executed, the executor will look to see if it is part of a frequently used loop. If it is, it will pause execution, snip out all of the opcodes that are part of that loop, convert them from Python opcodes into CPU assembly for your specific platform, and then paste them back in where they came from. This is extremely complicated, but also extremely useful. All right, so we're back to executing our first opcode. We want to load something named print onto the stack. Like we saw 2 slides ago, that uses PyEval load name. In here is where we see the 3 lookup scopes that exist in Python. So first it's going to check the locals, then the globals, and then the built-ins. Now, our hello world doesn't declare any variables, local or global, so it's probably going to come from that third one, the built-ins. And indeed, in the list of built-in methods registered when Python starts up, we find one named print. Load name will push a function object referencing this onto the stack, and then that load const opcode will push our literal string hello world, and then we get to that call opcode. When we execute the call opcode, it's going to start running this function built-in print impl. Now, most of the code in there is dealing with parsing and validating the arguments passed into it because print is an extremely complicated function. But deep down, we see some of the shape that we expect. We're getting a reference to something called stdout from the sys module, and then we're calling write object on each argument in turn. We're 24 slides in. We've got to be close to seeing our hello world, right? All right, if we're getting a reference to stdout, where did that come from? When any program starts, it receives 3 special, already open file handles from its parent. These are standard in, out, and error, and they are respectively numbered 0, 1, and 2. Now, Python doesn't know anything about what's in those. All it's doing is grabbing it, wrapping it in some encoding and buffering helpers, and stores a reference in the sys module. Another small aside, we are definitely down in C code. We're going to be seeing mostly C code from this point out, but a lot of this reads really similar to Python. That is not by accident, and it is very useful. There are going to be some other things in there. You'll see ref counting, macros, and error checks. But a good mental trick when you are reading through Python's C code, you can usually just recompile this in your head into the equivalent Python. It makes it a lot easier to read. All right, once again, let's fast forward down the stack a little bit. We're going to see those encoding and buffering helpers that we wrapped standard out in before. We're going to eventually end up in this method pywriteimpl. Now, this is a core function. It's used for all kinds of file I/O inside Python, so it is absolutely covered in special cases for weird operating systems. Fortunately, Linux is pretty simple. All it's going to do is call this function write with the file descriptor for standard out, which, as we said before, is 1, a buffer with the bytes in hello world, and the count of the number of bytes to write, which is 12. Don't forget there's a new line. This is the outer edge of Python. We could stop here, but what fun would that be? All right, to dive into the write function, we need to talk about libc. Libc is a standardized API exposing helper methods, operating system interfaces, math functions, and lots more stuff. Libc is really just a specification. Anyone can implement write. All you have to do is implement some kind of function that matches that declaration. But it's been documented and formalized a few times. Most commonly is the Portable Operating System Interface, or POSIX specification. So when you hear POSIX, that is a type of libc specifying document. Now, in terms of implementations, we're usually going to be using GNU libc, which is shortened to glibc. You will, just for completeness, sometimes also see muscle. If you ever use the Alpine container images, those use muscle instead of glibc, but we're not talking about muscle today. All right, this is the implementation of write in glibc. We see the expected 3 arguments, the file descriptor we're writing to, the address, the number of bytes, but this function's not really doing very much. It's just forwarding our arguments to something called a syscall. What's that? Our programs cannot be trusted. All normal programs run with a bunch of hardware-level security restrictions. For example, we can only read memory that is assigned to our process. We can't just willy-nilly start reading from someone else's RAM. That would be very bad. This is called user space. It is incredibly important for digital security, but sometimes we want our programs to be able to do something a little bit more dangerous, like touching a file. So there is kernel space. This is a different mode when you are running the actual kernel, the core of the operating system, with all of its elevated permissions. Okay, back to syscalls. A syscall you can think of as the window in front of a bank teller. It is a way that you can pass a request into the kernel to do something using all of its fancy permissions on your behalf. Just like at a bank teller, you can hand them a dollar bill, but you cannot jump over the counter and do whatever you want. All right. glibc has a couple wrapper functions to get through in the call stack because write is a special kind of syscall called a cancelable syscall. For example, you could have a blocking write that has a timeout in user space, so we need extra helpers to be able to smoothly abort it just in case. But eventually we get to the syscall itself. Now this is written in assembly for each language, for each platform that glibc supports. For x86 64, the way syscalls work is that you put the syscall ID into the RAX CPU register. That ID is going to be 1 for write. Then you put your other parameters into a bunch of other CPU registers, and then you make the syscall hardware instruction. That tells the hardware to jump into kernel space for you. As we land from the syscall CPU instruction, we are now inside the Linux kernel. We are running in kernel space. We have unlimited cosmic powers. There is a single landing pad for all syscalls, and inside that is a dispatch table. So it's going to look at the RAX register and figure out what syscall was this and where should I send it. Syscall ID 1, that's write, that is mapped to the syswrite function inside the kernel, which is a one-line wrapper for ksyswrite for some reason. What that's going to do is look up our file descriptor in the list of files that the kernel has been kindly keeping on our behalf behind the scenes. This is the literal meaning of file descriptor 1. That means that we want the second entry in that files list. Then it's going to pass that down to something called VFS write, short for virtual file system write, because we are now in VFS land. Just like we had a dispatch to a callback based on the syscall ID, we're going to do that again, but this time based on what type of file it is. Roughly 1 million years ago, I said that our Python process receives its standard out from its parent. Now, it's usually going to be a shell of some kind, bash or ZSH or fish if you're extra fancy, but what did it give us? The os.fstat method lets us investigate any open file descriptor. So looking at standard out, we can see it's got a funky file mode. That identifies it as a device file, which is how Linux exposes drivers. Each device file has a device number, which is broken down into a major in the high byte and a minor in the low byte. So here we have major 136 and minor 0. This is new information, but doesn't really tell us anything about what this file is yet. To figure out where VFS write is going to send our call, we need to look at the device driver registrations. So these happen in the kernel at startup. Each subsystem can register a driver with a given major and also attach a set of function pointers to that device driver. So because our file has major 136, it is going to populate the fops or file ops in any open file handle with these functions. So we can see that the next stop for our write is tty write. In the olden days, the way you interacted with a computer was through a modified electric typewriter called a teletype. This is a way to send input to your program by typing on it and receive output by printing to literal paper. This one here was the Model 33. It was quite snazzy for 1963. Teletype eventually got shortened to TTY because our industry has literally always been like this. But I'm guessing most of you don't work this way anymore, or at least I hope not. Usually we'll instead have a software terminal, xterm, terminal.app, command.exe. But because everything in computers is built on the bones of the past, we've left all of the terminal interfaces pretty much unchanged since the 70s and just added an emulated version. This is a pseudo TTY, shortened to PTY. For the most part, it's just a fancy pipe. Anything that you write into one side, you read on the other. In terms of implementation, this means it's a shared memory buffer of some kind that one side can write into and another can read from. Technically, this is also bidirectional. There's one buffer for each direction, but we're only looking at output, so we're just going to kind of skip past that for right now. This is what our standard out actually points to. It is a PTY device running in Unix 98 compatibility mode. All right, back to the kernel. In our call stack, so VFS write is calling to TTY write, which is then going to call into PTY write. And if we go one layer deeper, we find the somewhat wordy TTY insert flip string flags. This has a call to the helper function memcopy. So in here, we have our helper string in chars, and we have our memory buffer in TB. This is the final destination for our print. This is where it's actually going. But there's one more step. If you're familiar with C programming, you may recognize memcopy as a helper function to copy bytes from one location to another in memory. However, the kernel cannot depend on libc because that would cause an infinite loop. That is bad. So the kernel has its own implementation in assembly. Hello world plus a new line, as previously mentioned, is 12 bytes. So we're going to end up in this section of the kernel implementation of memcopy, designed for copying between 8 and 15 bytes. So the final destination for our hello world is these 4 moveq instructions. That is short for move quad word. This is it. This is where our hello world ends up. We could technically go even deeper. We could look at what transistors implement moveq, or how do transistors work at all. Unfortunately, AMD and Intel don't actually release very much information about how their cores work anymore, so I'd have to get really hand-wavy. I think this is probably as far down as we can go today. All right, our write has completed. We're going to rush back up the stack. We're going to see every layer in reverse. we clean up some kernel locks, we jump from kernel space back to user space, we finish this call opcode, our print function returns, we've been in this for 20 minutes, the REPL loops and just waits for future input. But okay, we kind of skipped, we showed where the write goes, but how does it get to the screen? All right, we talked about PTY is just a fancy pipe. One side writes, another side reads. Okay, so in our terminal application, it's going to be reading in a loop somewhere. This is going to use the read syscall. That's going to dive all the way back down through libc into the kernel, make a syscall, get to the TTY subsystem, the PTY subsystem. It's going to eventually find that exact same memory buffer as we copied our hello world into, and it's going to do the same thing in reverse, return those hello world bytes all the way back out to our terminal program, and then your terminal program will have to render them on screen. Exactly how that works is up to your terminal. Here's just an example from Xterm. And so, at long last, we can see our hello world exactly as expected. Simple, right? All right, so why do we care about all of this? Everyone here could probably have told me what Hello World does. This wasn't a puzzle to be solved. Programming is full of amazing abstractions, and we couldn't build things without them. But there will come a day where every single one of those abstractions will fail you. Maybe your program is crashing in a weird new way, or you need to squeak out a little bit more performance out of your web app, or something new we haven't even imagined will fail. Everyone should feel comfortable peeling back the layers of abstractions until you find what you need. This was certainly overstatement for dramatic effect, but I've had to work with basically every one of these layers at some point in my career, except Xterm, so far. Play with your tools. Tinker, fix, experiment. You aren't just a Python developer, you are an everything developer, and inside every abstraction is a new lesson to be learned. Thank you very much.
Thank you very much for that, Noah, for that well-went tour through the Python internals. I was going to make a joke about quantum physics, but you already took that away. We do have plenty of time for questions. If anybody's brain is not as scrambled as mine after this, please raise your hands. Yes, just wait for a microphone here.
Not a question, but I've used Forth. How dare you? And I am old.
Thank you.
All right, any other questions? Let me have a quick look to see if we got questions on Discord.
So of course, why is Python slow? We are built on a stack of abstractions of abstractions of abstractions.
So many.
Which ones of those could we strip out if we actually started clean and make Python fast all of a sudden?
I mean, so there are a suite of technologies, it's not really one thing, but unikernels are a way to try to build all of this into kernel space. I do not believe there are any currently active Python unikernel projects. There were in the past. I think they are all sleeping right now. Most unikernel work is being done in OCaml and Rust at this point. So the idea being that if there is only the kernel, there are no syscalls. We can just dispense with all of that weirdness and dispatching and just compile it all into one thing. That is certainly a very compelling story. I don't think any unikernel project has quite worked out a set of smoothing tools to make this not extremely disruptive, but certainly if I needed absolute maximum performance, that is the direction I would go.
Awesome talk, Noah. Thank you very much for that. Have you got some time just to go and talk about the JIT side that you briefly went over? If you can take another half an hour, that would be really appreciated.
I slightly understand the JIT. I'm not sure I am qualified. So the general idea is what I said. So it's looking for hot loops. So it means that the first time it runs a jump backwards, it's not going to do anything. It waits until a certain threshold of identical jump backwards have happened. So in each jump backward opcode, it is basically keeping track of how often have I run. And if it sees, oh, this jump backward has happened 50 times in the last, 1,000 instructions, okay, this is probably a hot loop. You've got a for loop or a while loop that's going really fast. So that's what activates the JIT, as far as I know. And so it will pause, it will try to, so this is the opcode level, so it doesn't really know what a for loop is anymore. That's already been expanded, but it's trying to reverse engineer what probably was the body of the for loop, put all of those opcodes into an array, ship them off to the actual JIT thing, the thing that turns the opcodes into assembly, which itself is kind of complicated, but you can imagine how that works. Like that's just doing all of the same code as the opcode execution would be, but hardwired into assembly. And then there is a special thing that it can shove back where the opcodes were that is, no, actually, please just literally jump into this block of assembly. I promise it's safe. That's basically how the JIT works, as far as I know. It is evolving extremely rapidly. So again, if you are watching this on a video and it is past September 2025, please go check the documentation because it might be something new by then.
All right, another question in front here.
Yeah.
PEP744, if you want to look up more info about the JIT, and I'll chuck a link into the Discord as well.
Highly recommend. She is far more knowledgeable than I.
All right, we've got time for one or two more questions if there are any. No? In that case, let's all give another hand to Noah for his wonderful talk.